Welcome back to the class on electrical machines too. In this lecture, we are going to discuss about the classification of single phase induction motor and double field revolving theory. Why should you go for the single phase induction motor? For the most of the economic reasons, suppose if you see the houses and offices and very rural areas where only the single phase supply is available. Suppose if you want to use any motor means then you have to go for the single phase induction motor only. Because where the AC supply is available, that's why we have to use only the single phase induction motor. We cannot use the three phase induction motors. The fixed load requires not more than the 0.5 kilowatt can be generally served by more economically by means of a single phase induction motor. The single phase induction motor construction is very simple and reliable. Easily we repair and replace it also. It is cheaper cost. Single phase induction motor can be used in fans. Generally, in our houses also we are using fans and refrigerators, fridges, centrifugal pumps, tools, kitchen equipment, washing machines. All these household purposes we are using only the single phase induction motor. That's why it is necessary to study the how the single phase induction motor will be working. What is the construction of the single phase induction motor? First, we are seeing the classification of the single phase induction. The single phase induction motor can be classified broadly into two types. One is split phase induction motor, another one is the shaded pole induction motor. Another split phase induction motor, resistance start induction motor, permanent split start induction motor, capacitor start induction motor. Last one is the two value capacitor start induction motor. Another name for this one is the capacitor start capacitor run induction motor. If we come to the shaded pole induction motor, there are two types of there: reluctant start induction motor, repulsion start induction motor. Next coming classes we are going to see individually how the each single phase induction motor will be operating. Now we are going to see the construction of the induction motor. If you come to the construction of the single phase induction motor, it has a two parts. One is the stator, another one is the rotor. The stator is nothing but the part which is stationary. It is consisting of stator frame, stator core. Core is laminated to reduce the hysteresis and eddy current losses. The outer periphery of the core is slotted to house the single phase distributed winding. When you come to the rotor of induction motor is like a squirrel cage induction motor only. The rotor core is placed on the shaft of induction motor. The shaft is placed between the bearings because the rotor has to keep in the stator. The stator winding has two windings. One is the main winding, nothing but the winding which has a low resistance. One more winding is nothing but a starting winding. It also mounted on the stator. The winding has a high resistance, is embedded deep inside of the stator slots so that they have a considerable index. The rotor construction is same as a squirrel cage induction motor. Now we are going to come see the principal operation of a induction motor. Induction motor is not a self-starting motor as like a three-phase induction. Because in case of three-phase induction motor, whenever you are giving three-phase supply, the motor will be starting. But the same thing does not happen in case of a single-phase induction motor. That we are going to see now. See, this is the stator, this is the squirrel cage induction motor. Whenever we are giving the single-phase supply to the stator winding, the sinusoidal flux will be created. That is passes to the rotor. Whenever we are saying the flux lines are nothing but a closed line. Now, what is the physical meaning of sinusoidal flux means? This is the axis of the flux. In this axis, the magnitude of flux will be changes. From 0, it reaches the maximum value at 90 degrees. Again, it comes to the 0 at 180 degrees. The direction of the flux also will be changes. Again, after 90 degrees, it reaches the negative maximum. Again, after 90 degrees, come to the 0. That is the one cyclic operation of how the flux will be changes in an air gap. Whenever we are given the AC supply, the flux is creating from the stator. That is sinusoidal flux only. In the space, this is the space. In the space, the magnitude of the flux only changes, and also its direction also will be changing, but it is not a rotating thing. Suppose if we come to this diagram, this is the north pole because from this point the flux lines are leaving. This area we can take it as a south. Upper half conductors are lying under the south pole. All these lower half conductors lying under the north pole. This flux will be changes. So there is a rate of change of flux linkage with the rotor conductors. Voltage will be induced in the rotor bars. That voltage will be driving a current through the all conductors. These conductors are carrying a opposite direction of the current when compared to the conductor which are lying under the north pole. Because this is north pole, this is the south pole area. The torque developed on this conductor in one direction, the torque developed in the upper half conductors on a opposite direction. This torque will be gets cancelled. Finally, the net torque developed in a rotor will be zero. So that's why the single phase induction motor is not a self-started induction. Now we are going to see the double field revolving. In case of double field revolving theory, if any flux which is changing only in one axis, that we can resolve into the two fluxes has a magnitude of and which are rotating in an opposite direction. The theory make use of the idea of alternating uniaxial quantity can be represented by two opposite rotating vectors of magnitude. The sinusoidal flux can be resolved into the two components which are rotating in opposite direction with a speed of synchronous speed, but the magnitude of the flux can be half of the sinusoidal. Now we are going to see the first. This is the sinusoidal flux whose magnitude is pi m. Now this can be resolved into the two components. One is pi m by 2. This is another pi m by 2. This is rotating in this direction. This is rotating in a opposite direction. So try to observe here. This is the sinusoidal flux. So whenever you are saying the sinusoidal flux, the same axis, the magnitude of flux will be changes and direction also will be changes in a regular interval of time. It is not rotating, but these two components are rotating. That is the double field revolving theory. Here, you have to prove that the vector sum of these two rotating vectors is equal to the sinusoidal flux. Here we are assuming that one is rotating in a clockwise direction, another one is rotating in a anti-clockwise direction. In this instant, if you find the phasor sum of these two, so that is equal to the pi m. Now after some time, both are making an angle of plus theta and another one is minus. If you find the phasor sum of these two vectors by means of parallel theorem, you are getting the phasor here, that is the pi m cos. When compared to the first case and second case, the magnitude of flux will be decreases. In first case pi m, second case pi m cos theta. But the direction of flux is the same direction. After some time, nothing but now the first vector, this is the A vector we have taken, it is displaced by 90 degrees, it is also displaced by 90 degrees in a clockwise direction. Both gets cancelled, so the resultant flux becomes a 0. Nothing but the magnitude of sinusoidal flux becomes a 0 after 90 degrees. Now, if we take the one more case, now again from the previously this vector is at this position, this vector is at this position. Now both are displaced by 90 degrees. Again, if you find the phasor sum of these two, it gives the resultant flux in this direction. Nothing but now the direction of the flux, sinusoidal flux will be reversed, whose magnitude is equal to sum of these two, that is, this is minus pi m. After 90 degrees, again the resultant flux becomes a 0. Again, rotation of after 90 degrees, here it comes to the original value. On the x-axis, if you take the theta, on the y-axis, if you take the flux, every 90 degrees, if we find the resultant of these two rotating components, if we find the resultant flux, that we have to take on the y-axis, and if you plot a graph, we are getting this type of plot. 0 degree maximum, 90 degrees to the 0, again after 90 degrees negative maximum, again after 90 degrees, again it comes to the 0. This point is represented this way diagram. Now we are assuming that the sinusoidal flux has a two rotating fluxes which are rotating in a stator, both are rotating in opposite direction. So when these fluxes are rotating in a stator, there is a rate of change of flux linkage with the rotor conductors. There is a voltage will be induced in a rotor conductors due to the forward flux, another one is the backward. See here what is the flux we are going to take, it is a forward flux means the flux which is rotating in a clockwise direction, that we have taken as a forward flux. The flux which is rotating in opposite direction to the forward flux, that we have taken as a backward. So when these two fluxes are rotating, there is a voltage and induced in a rotor conductor, the current is passing through the rotor conductor due to the forward flux as well as a backward. There is a torque developed in a rotor in the forward direction due to the forward flux. Opposite direction also a torque is developed due to the backward. These two torques are equal because the flux are equal. So the net flux at the time of starting becomes a 0. So the single phase induction motor is not a self-started induction. Now here we are going to see mathematically and graphically also why the single phase induction motor is not a self-started induction motor. Already we know that the power developed by the rotor is P is equal to 1 minus S by S into I2 square into R2. I2 square R2 by S gives the air gap power into 1 minus S, which gives the gross mechanical power developed in an induction motor. The torque developed in an induction motor, that is equal to this quantity divided by 2 pi n, nothing but angular velocity of a rotor. This n we can write it as a ns into 1 minus s. So in place of n, if you substitute the ns into 1 minus s, the 1 minus s and this 1 minus s gets cancelled. Finally we have a k into I2 square R2 by s. This is the gross torque developed in an induction motor. If you want to find out the torque developed in a single phase induction motor due to the forward flux, then Tf equal to k into It square R2 by s, where s is nothing but a slip of the forward flux with respect to the rotor. So if you draw the slip torque characteristics of a forward torque, this is the profile of the graph. Slip for the backward flux, you have to take the minus ns minus n by minus ns. To simplify this one, finally you are getting the 2 minus s. Now the backward torque equal to, in place of s, now you have to substitute this one. You are getting the backward torque equal to minus k into I2 square R2 by 2 minus s. The total torque developed in a single phase induction motor, that is equal to forward torque plus backward torque. Now you add this equation and this equation. Finally you are getting the k into I2 square R2 by s minus k into I2 square R2 by 2 minus s. Now we want to find out the how much is the torque developed in induction motor at the time of starting. So I have to take the s equal to the 1. If we take the s equal to 1 in the above equation, now the starting torque developed in a single phase induction motor come to the 0. This is the profile of the graph of a torque developed in a single phase induction motor due to the backward flux. So we are calling it a backward torque. Starting torque is nothing but a where slip equal to 1. This is the point where the slip equal to 1. The magnitude of the backward torque and magnitude of the forward torque both are equal. If we find the resultant of these two graphs, at this point this value becomes a 0. So the net starting torque developed in a single phase induction motor becomes a 0. So we can say very easily that single phase induction motor is not a self-started induction motor. In this class, we have discussed about the why you have to use a single phase induction motor and construction of a single phase induction motor. Why the single phase induction motor is not a self-started induction motor. Next, we have discussed about the double field revolving. From the double field revolving theory also, we proved that the single phase induction motor is not a self-started induction motor. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of my YouTube channel, so that I am always welcome to answer all your questions.